Hello.
Hello.
So how are you doing?
I'm doing all right. How are you?
I'm okay. So how many classes are you taking?
Just for this semester.
Oh, I see. That's not bad. How many credits, if you don't mind me asking?
Just 12 right now.
That's not bad.
Yeah, I mean it's doable. I gotta work, so I tried to keep it a little simpler for myself, especially since getting back into it all after like 6 years. So
Yeah, actually for me, I started fall of 2014. I was supposed to graduate 3 years ago, but it didn't work out.
yeah, that's how life seems to go.
I actually took this class like 3 years ago, but I had to drop it. Um,
Yeah, it was like a little bit before that, but I took it and basically had to do the same thing. Just some crazy stuff was going on, so I just kind of dropped out of school for a while and spent all this time just catching back up, basically.
Looking at a classroom. So apparently we will have to move from here. So
From this room?
yeah.
For what reason?
Because the number of occupancy doesn't match the number of,
Oh, really?
yeah.
Okay.
So it is wherever I was right in front of the building. So that's what it is. Is it too inconvenient for you?
I guess. I've never been in that building, but.
Yeah, you'll
I
get
don't think
used
that
to it, even it's inconvenient for me. Hello? Are you guys there?
hey,
Hello.
Hey. So let's see, we have, let me try to change the view here so that we have Bowden in the room. Hey, Matt, yeah. Yeah, it's good to put on the videos, yeah, if you can, but I won't insist because there are privacy issues also, right?
I'll keep it on.
Yeah, I'll encourage it, but at the same time, I understand if you're not interested in always paying attention, it's easier to just switch it off. So yeah, feel free to put it on. How about that? Yeah.
Yeah, I got to work on my camera angle. It's a little close, but as for now, I'll keep it on.
Yeah, we see all the features. Hi, Wahid. Yeah.
yeah, hi. Actually, last class, my audio wasn't working. I actually had some dust in my, like, for my physics 430 class, so I had to vacuum it out.
Okay. But it seems to be okay now. I can see you and hear you very well.
Yeah, I wanted to say if you could hear me well, and I can hear you.
Yes, I think this is good. And Christian, that's good. Yeah.
Yeah,
Okay.
sorry, my younger brother was in town earlier, so we did lunch. So I spent, an extra 15 or 20 minutes instead of driving to Carbondale from Murfreesboro. So yeah.
Perks of going online. Yeah.
Exactly. Yeah. I had the option too, so it was okay.
Okay. So here is a update on whatever we were, like I sent you an email about if you can give me a consent about extending or making sure that we don't occupy this room more than 5. So it did get approved, and Matt and Jeremy are able to enroll in the course. They have already enrolled. So that's the good news. There is a small bad news to this, is that we have to move the classroom anyway. Okay, so they told me that, oh, if everyone gives it in writing, it's okay. But then they decided that no, occupancy is more. Now we have to move the classroom. Okay. So if, first of all, I should say, Travis and Wahid, if you could still give me the consent, that's good. Because in one of the emails, it was said that all 100% of the students gave consent. So do you give it to me just as a liability thing, if you don't mind?
Yeah.
Okay,
I'm submitting
and the
that right
second
now.
thing-
I forgot. That's my bad.
Yeah, please do that, because I told the administration that all the students agreed. So you guys did mention it in verbal. So I don't think it'll ever become any issue, but still, yeah, I would like to have it if you don't mind it. The second thing is, yeah, the classroom has been moved. So that means, I mean, most of you, if you're planning to attend online, it doesn't bother much. But we are now moved to a bigger classroom for sure, but it's not even in the same building, which means I had to take all the camera setup and everything and move. So it's in Parkinson's laboratory. Do you guys know where that is?
Maybe.
That's a geology building.
I haven't had any classes over there. I'm not sure.
Yeah, so do you know, if I'm talking, so it's the west end of the student center. There is an administration building, if you know, right? And it is right on the west side of it. I can draw
Yeah,
this.
so like the student
Yeah,
services building, it should be right across,
That's correct.
like with that long walkway.
Like by Feiner.
Yeah, from Finger to East Campus,
Mhm.
like right along that.
Okay.
Also, I should be saying north side of the center, right? Student center, not the west. Yeah, north. I think it's not. Yeah, let me draw this in. Yeah, I can use this.
Yeah,
That seems really inconvenient for you, especially Dr. Shajesh, with the.
Yeah, but yeah, I mean, see, these things I cannot mention, right? I requested for a room. First, I was very happy that yes, okay, if it is just a consent, nothing changes. But then when you say this is what it is, then I don't want to bring in an alternative that no, this is very inconvenient for me. So they'll drop the whole idea then. So I didn't want to say anything. So it's okay, I'll manage. I think I'll get a bag or something and start moving the camera or something. If it is too heavy, I'll take help from you guys. But I think I should be able to manage. I still can manage, I think.
Yeah,
So we'll see.
I just sent an email, so
Oh,
I
sure.
responded to the email.
Yeah, thank you, Wahid. Yeah. So that's just for paperwork. Yeah, I don't know. I don't expect any. Okay, so let me move the camera and I'll show you the. So let's decide that from Monday onwards, we will have the classroom there. So all of you are welcome to come. There is no restriction now anymore. If you think you want to be in the classroom, you're welcome there. If you find this way, that's okay. It's up to you guys. Okay.
What was the room number at Parkinson's?
Yeah, I'll just tell you. Give me a second. Let me change.
Okay.
One thing at a time. Actually, if you now go to the class scheduling, it actually lists that. So that's another way of finding out. But I'll let me zoom in. Okay. So this is 1 and 7.
It says 108 built or Parkinson room
That's
108.
correct. That's correct. So let me draw this. So let's me try my abilities here. So this is the student center. This is a long building, I suppose. Can you guys see this? Maybe change the pen. is nectar, I suppose, right? I think it's in this shape somehow, if I'm not wrong. Is that clear? Is the reference there? So there's 51 somewhere here, I guess. Now this is the administration building here. And probably Fenner is like this somewhere here. Is that correct? Bowden, correct me?
Yeah.
So this is the building we're talking about. This is park. They have the notation park. And the room number is 108. So when you enter the building from this side, so that's the entrance. If you enter, it is right on the same floor. It's, I think, the second room to your left. So you go enter the building, turn to your left, and again on the left you will see room 108. Pretty easy to find. It's a reasonably, reasonably means it's slightly bigger than this, but here we have tables. I think that's what makes it more restrictive. I don't know. I think the way I think they calculate it is that the number of students that could occupy before, then you divide it by 4. That's how they calculate it. But it is bigger than this, probably double actually. Yeah. So it is. It has a nice blackboard, so that's a good part.
Well, it's good everybody can attend, like everybody was able to register.
Yes, I think now registration part is over. Now, as far as attending comes, it's up to the choice, right? It's up to you guys. I remember that the COVID situation is still there, so be judicial about that. That's your decision. If you think studies are more important than health, you come to the class. If health or spreading is more important, then that also works. It's a small price to pay. I think online is also possible. Okay, is that clear enough? So the room number is again Park 108. From Monday onwards, we meet there. Okay, all of us are here today. 1, 2, 3, 4, 5, 6, 7. 7 of us enrolled. All of us are here. So Curtis, you're there, right?
Yeah, I'm here.
Yeah. Okay. So yeah, all of us know this. So okay.
Just to double check, it'll still be offered online, correct?
Yes. Everything stays the same. It's just that I moved.
Got you.
If I understand, like Curtis and Travis, you prefer to be online, so that doesn't change. Others, I don't know. I think Matt, you also preferred online, right? Last semester.
Yeah, my girlfriend's got is like a higher risk. She got a hyperactive immune system, so and my mom's also got some underlying health conditions, so I'm fine, but if I'm gonna be around them, I gotta be careful. So.
Yeah, sure. But others, it's up to you guys what you want to do. So that's the point. Okay. Okay, let's proceed. Set this for once. Okay. Few things. Do you have a homework due on Wednesday? And there is a quiz whenever I mention a problem in the class. So maybe I should say that by chance, if I don't mention any problem in the class, on that day we won't have a quiz. Earlier I used to say that still write something saying that you didn't have a problem and I'll give a grade for that. but no more of that, because then the maintenance is higher, like then I have to organize that, okay? So if there is no question, then there is no quiz submission. And I'll just delete that from the grade book. Yeah. Question? Someone said?
Yeah. Is the submission closed? I actually completely forgot to submit it. I wrote up the cyclotron thing. Could I email that to you? Is that okay?
Yeah, send it as an email. Like if it is once in a while, do this. Whenever the submission is closed, just send it as an email. But if I see that the same person is doing this every week, this is happening, then it's too much work on my part. Right? I don't want this maintenance too much. So once in a while, yes, do feel free to do that.
Thank you.
Yeah. And same thing holds for, I think, anyone of you, if you have missed the deadline, it's the first quiz, so feel free to submit it. Okay. There's also midterm 1. Where is this? Oh, February 19th. And again, classroom switch. It is some laboratory room 108. We were doing how does a charge behave in a magnetic field, and we said that we would also like to extend to what if there is an electric and magnetic field. So let's get to that again. This charge in a uniform magnetic field. Two variations you can make. You can say non-uniform in position and non-uniform in time, but those are problems. See if we can do that later. Right. So we said there is a magnetic field. Did I make it go inside, or I think I said coming out of the board? That represents a magnetic field coming out of the board. Now let's say there is a coordinate system. That's the coordinate system. That's X, that's Y, and Z is coming out of the board. And let's say the magnetic field is actually in the direction of Z. Let's say P, Z hat. I sometimes say K hat for direction of Z. Sometimes Z hat, I keep switching around. We are also say there's a positive charge. It's a positive charge, and at time t equal to 0, its position is R. Its position is R at time t equal to 0. It's 0. So it's right at the origin itself. If you want, you can say this is 0i plus 0j plus 0k. And its velocity at time t is equal to 0. Let's say that is moving in the y direction. That's your velocity v at time t equal to 0. And let's say that this is v naught. So it's in the j direction or in the y direction. So that's v naught times j hat. That's all. And I say k. Oh, I already switched. Okay. That's your information given to us, and we would like to know in what direction does it go? We already pointed out that this is going to go in a circle. So that's your circular motion that's going to happen. Right? Obviously, the center of the circle is somewhere here. So it's not the origin, it's somewhere here. And we should know what's the radius R of the circle. And how often does this go around the circle? So that's the idea. And the direction of motion is this, and that's the magnetic field all around. Okay, so our equations of motion are mass times acceleration. V by dt is equal to q v cross b. So here, this is an example of a force where the force depends on the velocity. And we pointed out last time that another force that depends on velocity is a drag force, right? And we talked a few things about that. But coming to magnetic force, this can be rewritten as dV by dt. Oh, am I out of the board?
Yes.
Oh, so yeah, okay. Okay, so that's dV by dt. Write this as V crossed with. So let me define B times Q over the mass M as omega. This omega is good enough, but it's good to stress that this is the cyclotron frequency, a very important parameter when you're talking in terms of magnetic field. So the magnetic field is the moment you talk about a magnetic field, the cyclotron frequency comes in because a charge starts going in circles, and you talk about how often does it go in circles. So a good point to think about is, yeah, quiz, right? Yeah, quiz. Right, so notice that the cyclotron frequency is completely determined by the charge and the mass. Correct? So you can ask the question, what if you have a magnetic field, given a magnetic field, let's think of Earth's magnetic field. What is the strength of Earth's magnetic field? Anyone?
Is it like 10 to the 7th, something?
Units matters, something doesn't help. Yeah, it is 10 raised to minus 7 in some units for sure. Yeah, but try again. What's the unit of magnetic field to begin with?
Tesla or Gauss, right? It's
Gauss or Tesla. Good. Right. So in Gauss, it is 1 Gauss. Right? That's the magnetic field of Earth, like on the surface of Earth. Of course, if you go away from the surface, it gets weaker as you get closer into the Earth. That gets stronger. But then it is equal to about 10 raised to minus 4 Tesla. Okay. Yeah, and in milliliters, right? It's 10 raised to minus 7, so it's correct. 10 raised to minus 7, right? In a sense. Yeah. So, but it's that's your. So let's say that's your magnetic field, and let's say there is an electron that's floating around in the atmosphere, and if it is moving, then it will start going in circles around this magnetic field. Correct? And immediately you should be able to find out what is omega c. How often does an electron go around in this magnetic field, right? You know the charge, you know the mass. So you should know that, right? So find omega c for electron. For electron, R goes with 4 for electron, right? Find out what is omega c for proton. These are the two important, and maybe I can add one more question. Omega c for neutron. That you should be able to answer right away. What is the cyclotron frequency for a neutron on the surface of Earth?
0.
0, right? Yeah, Q is 0, so that's But it's good to know the difference between them. Electron and protons behave very differently. If you want, you can extend this further, right? Extend this further and ask what is the radius. Like if they're going in circles, it's good to know, does it form a 1 kilometer radius, or is it a millimeter radius, or is it a micrometer radius? Like when electrons are going in circles, how big a radius it is. I mean, you should be curious about it, right? And where do you see all this? This is all this digressions. I didn't plan to say this. Where do you see all this? So yeah, let's talk about this. So where does the magnetic field play an important role? So let's say this is Earth. Where is the north pole, magnetic north of Earth?
It's off, right? It's not. At
Yeah,
the
it's
actual
not on the North Pole, it's in Canada, right? It's somewhere in Canada, right? So this is the North Pole. This is the geographic North Pole, but the magnetic North Pole is shifted by an angle about, I think it's 23 degrees, if not 11 degrees. Check it out. Probably 23 degrees because it is all the way Canada, right? And it is not the North Pole, it is actually the South Pole. South, geographic South is somewhere here. Right, so this is the geographic south, and that's the South Pole, and somewhere here, so across the diameter is the magnetic north. So if you were to draw the magnetic field lines, so they go like this. They all come down here like that, right? Okay. But what is the essence of this? What I was trying to point out is somewhere here is sun, right? So this is sun. Sun is, if you have to describe sun to someone in a very trivial way, it is a huge ball of fire, correct? And it's a huge ball of fire means the temperature is so high that most of the atoms are not, they cannot stay there because the heat of the sun is larger than the ionization energy of most of the atoms. So they break apart all the electrons and protons. So in an atom, electrons and protons cannot stay together. They just separate them. So electrons and protons are separated out. And so if sometimes when there is a flame, some part of the flame are thrown out, right? If you've seen the fire, some part of the flame gets thrown out frequently. And that's called a, what is that called?
solar flare.
Sunburn, what is it?
Is it a solar flare or is that something
Yeah,
else?
solar flare, exactly. That's what I meant. It's called a solar flare. Right? And it's random. Like if you have a fire, when does a small spark from a fire get thrown away? It's extremely random. So solar flares are very random. So that means there is at that time, there is a beam of positive and negative charges get thrown out of this from away from the sun. And sun itself has a magnetic field. The moment it gets thrown away, they start going in the circles. But eventually, if they come and hit the earth, they start going in circles. And which side they will go, it depends on what's your initial velocity. It could go either this way or that way. And they will go in circles and they get guided by this magnetic field. And all these high energy particles enter Canada. Right? We are all saved down there. All the Canadians take all the hit, right? And what you see is it's a beautiful spectacle in the sense that the sky gets lit up because all these high energy particles come into the sky and they basically burn in very trivial terms. They basically burn. And that's what is known as what, northern lights?
Yeah, Aurora Borealis, I think.
Yes, exactly. Northern lights or Aurora. How do you spell it? I don't know.
Yeah.
I'll try Borealis, I think. I'm not sure.
Yeah, I think that's it.
Okay. Yeah. And there is a similar one in down south. Like I think that's, what is it called? I think the word is different. there. And notice that it's very random event. Like often it is advertised that, oh, if you go there, you'll see it, but you might spend all the money and you'll never see it. So if you're just traveling, be aware that it is very random event. Has anyone seen Aurora? Right. Yeah. Yeah, I have also. I heard that it's a kind of cool thing to see. Apparently, the best place for us is up in the north somewhere, Minnesota region. What is that? This can get stretched, so this whole region can stretch itself. So it can come down all the way to Minnesota if it's a big flat. And these flares are not very cool either. It can actually hurt our electric grid, right? That's what you would say, grid. The power supply grid that we have, that can get affected. It can pretty much shut it down. It has happened in the past about once or twice in the past 50 years. The electric grid, the half of the country or half of the continent has been without power. So that's yeah. So that's some information. But let's get back to our equations, right? Okay. So yeah, what was the, yeah, I wrote the quiz, right? Just find the angular frequency of electron and proton. Okay, so that's your omega c, where omega c now is equal to magnitude omega c times k hat. And we expanded this out and wrote our equations as, it's visible, yeah. As you can break this into three components. So that is dvx over dt. That's equal to vy times omega c, right? dv, the y component of acceleration is equal to minus vx of omega c. And the z component does not experience any force. If there is no force, that means it will just drift, right? If there are two solutions, either Vz is a constant, or it just means that Vz is equal to constant. So if it is zero, it will stay zero, which is what is needed if you want to go in a circle. If it is not zero, if it is a constant velocity, then it can get drift in the z direction. So it will maintain the circular part, but then it will drift upwards. So that's it forms a helix. Right, that's the idea. But let's for a moment say that, or not moment, right? We said that there is no Vz equal to 0 at time t equal to 0. So this is 0 actually. So at time t equal to 0, the z component is 0. So this has to be equal to 0. Notice these are coupled. The x component of acceleration is determined by the y component of velocity. And y component of the acceleration is determined by the x component. So it's coupled equation, but we can substitute one in the other. So substituting one in the other, we get dvx over dt. No, I want to substitute x, right? So x is minus dv by dt. So this is equal to dy dt of the vx is using the second equation, minus 1 over omega c times dvy over dt. That's using the second equation, and that's equal to vy omega c, which can be rewritten as, this implies that there's a constant, take it to the right hand side, second derivative of velocity, the derivative of acceleration, the rate of change of acceleration is equal to minus vy, or not, write it the other way, minus omega c squared times vy. Same thing you do with the second equation. This time I substitute the velocity, which is plus 1 over omega c times dv x over dt square. Is there a mistake I'm making? Y, no, I'm substituting y, right? That's plus, yeah, and that's, yeah, it's okay, good. That's equal to minus Vx times omega c, which implies second derivative of the x component is also satisfying the same equation. Okay? That should be a familiar equation. If you have an equation like this, it means that the second derivative of a quantity is a quantity itself. It's a constant, but second derivative of a quantity is a quantity itself. Which functions satisfy that?
EX. EX.
Yes, exponential. Good, very good. So exponential satisfies that. And since we are talking in terms of t, time, so it is exponential of time. And we also want this constant out, so we want to have exponential of omega c times t. But often in these matters, exponential, remember, is related to sine and cosine, like trigonometric functions. So trigonometric functions are also good solutions. Right? So this is an oscillatory differential equation for oscillations, and exponentials are good. Sine and cosines are also good. So for our purposes, let's write the solution as Vx as a function of time now. Right, let me stress the point that it's function of time is some cosine of omega ct. Notice that if I take the derivative of first derivative, I get a sine. Second derivative, it again becomes a cosine. But each time I take a derivative, omega c comes out, and it gives me that product. So that's a solution. But actually, sine also is a solution, as I pointed out, or exponentials of solutions. Right? But since there are two independent you need for a second differential equation, you can put a constant there in front, a plus b. We don't know what kind of combination it is that is decided by your initial conditions, and initial conditions are position and given in terms of position and velocity. What about Vyt? That also satisfies the same differential equation, but that's an independent quantity. Right? That's an independent quantity. So in principle, I should write a new coefficient, right? I think C won't confuse it with cosine. So this is cosine omega ct plus d sine omega c t. But we have to be careful in the sense that at time t equal to 0, they have to satisfy your initial condition. But before that, we know that these two are coupled. These are coupled in the sense that when I take the differentiation with respect to one, I should get the other. Right? So let me start with, I should probably move the camera. So let me start by calculating the x over dt, right? And in fact, let me calculate Vx over dt over omega c, right? This we know is supposed to be the y component of velocity, but let's start from x component. When I take the derivative, I get a minus omega c a, but omega c I divided it out, so it's minus a sine omega ct. And this one is plus b cosine omega ct. The derivative of the x component is cosine becomes sine cosine, with the sine getting a negative sign, and that should be a coefficient omega c, but I divided out by either. That's supposed to be the Vy according to one of your equations. Agreed? And this has to match this. Right? That's a constraint now. That means to say that d has to be a because sine omega t coefficient has to be the same, and c has to be equal to b. Right? So one of the equation puts a constraint on this. So we learn that A is equal to D and B is equal to minus cosine, right? Hold on.
Yeah.
Yeah, B is equal to, yeah, please, go ahead.
A is minus D though, right?
Did I say it wrong? Oh, A is minus D, yes, thank you. Yeah, thank you. Yeah, so let's say D is equal to minus A and C is equal to B, right? Good. Oh, it's equal to B. Thank you. Yeah, okay, so that's immediate learning. So now out of 4 unknowns, we are having only 2 unknowns, but we also know that velocity Vx component of velocity at time t equal to 0 is equal to 0, right? So if I use that in the first expression, so I get 0 is equal to A plus sine omega t plus 0, right? So I immediately get A is equal to 0, which immediately sets D is equal to 0, right? So that also means that that's equal to D, right? So that's equal to minus D, that's equal to 0. So many things are gone now, right? D is gone, A is gone, and I don't have any information about B, but I can get some more information. Remember, Vy is there, right? So Vy at time t equal to 0 is equal to V naught. Right? Set that Vy is again 0 is equal to, this goes away because it's a sine function, and B, right? So it is plus B. Oh, what happened? Oh no, it's not 0, right? It's V naught because it's a Y component, that is survival there. So that's plus B. So we know B. Now B is equal to V naught. So we have all the velocities now. Right? So Vx as a function of time, Vx as a function of time is equal to A is 0, B is V, so that's V naught sine omega t. And velocity with respect to, or the Y component of velocity is equal to not A is 0, so but B is what survives, so that's V naught cosine omega t. And you can test it at time t equal to 0, the X component is 0. At time t equal to 0, the Y component is V naught 8 volts. Okay, that seems to say, but still we don't know whether it's a circle or not, right? So we still have to process things. So let's move over. Okay. So we have velocity, which is dx by dt is equal to V naught sine omega t. Oh, I say omega, it is omega c, right? It is omega ct. I forgot to write the c subscript. And dy by dt is equal to V naught cosine omega ct. There's one thing we can learn immediately here, which is good to realize. That's Vx and that's Vy. This reminds us of the polar coordinates, right? Cosine of some angle, sine of some angle, which means that if I were to square this and add these two, so I square this, Vx squared plus Vy squared. What is that equal to?
V naught.
Right? It's V naught squared sine squared omega ct plus cosine squared omega ct, which is equal to V naught squared, right? Which means that the magnitude of the velocity remains the same. Like its components change, but its magnitude remains exactly the same, which is a signature of circular motion. But circular motion, of course, it doesn't have to be straight. Uniform circular motion, let's say, right? So it's a signature, but still we have not proved that it's a circular motion. It's a signature though of uniform circular motion. So let's come here and integrate this. Right now we can integrate this. So this is dx is equal to v naught integrate sine omega c t dt, right? Move the dt onto the right and then integrate. Now I integrate from some point to the other. So let's say I integrate from 0 to t. And when I'm integrating from 0 to t, I change my position from at t equal to 0, it's x0, right, which is 0, actually, like it is at the origin. So let's say x, yes, 0. And it goes to x, right? I've used the initial conditions here, which is x as a function of t minus, let me put it x0, right? In general, it's x naught, which is the initial point which will set it to 0 in a minute. That's minus x naught, that's the integration. And this is what? Cosine omega ct, no, minus, right? So minus v naught over omega c times cosine omega ct. At t equal to 0, x of 0 is equal to 0, right? So at t equal to 0, this is gone. This is 0. So that implies that x subscript 0 is equal to 0. Now it's still in the frame here. So this is not there actually, right? So this basically goes away using initial condition. X of t is just what's the dimension of velocity divided by angular frequency? What's the dimension of velocity over angular frequency?
It's dimensionless, right? No. Or no, it would have to be a length, right?
Length, exactly, which is correct because on the left side there's a length, right? So most probably that's a length. Let's call that r, right? We don't know what is that, but it will turn out that that's the radius of the circle. As of now, we don't know that immediately, but let's, so we have x of t is equal to minus r cosine omega ct, where I've defined the quantity r because it's an important parameter. Like remember in your, like this is more commonly written in this form, right? This probably is more familiar. Velocities omega times r angular frequency times this. Okay, that's your x, but now what is your y? Like do the same thing for y. Y naught to y dy is equal to v naught cosine, right? So 0 to t cosine omega ct dt. This is y minus y naught. Right, that's equal to v naught. So now what's the difference here? Again, you see v naught over. Did I do this correct? Any mistake here? I think there is a mistake. Yeah, can you guys see the mistake here? So from this, yeah, this step there is a mistake. Or here, this step there is a mistake. This conclusion is wrong. Can you check on that? Why I do this? What's wrong in this conclusion? At time t equal to 0, x naught is equal to x at t equal to 0, and then I said x0 is equal to 0. What's wrong in that? So at time t equal to 0, x is 0. So let's substitute that. So it is 0 minus x naught is equal to, at time t equal to 0, cosine doesn't go to 0. Right? Cosine of 0 is 1. So that's minus v naught over omega c. Right? So the x naught is actually not 0, right? So what does that mean, right? Oh, I mean, we said this is time t equal to 0. That this is an integration constant in principle. That's the way to look at it, right? So what am I saying here? That means this is r, right? So this is your r. So x naught is equal to r. So the point is, I should be careful in interpreting this constant here. So that's going to come out as the center of the circle. So this is equal to x of t minus r. Correct. And similarly, when I do this, I should be careful here. Right? I think that's where the catch comes. This is help me here. Yeah, I think let me do this properly. Okay, so this is because otherwise the interpretation goes out of the window. Right? So this is initial condition x0. So this is x of t minus x naught is equal to, this is minus v naught over omega c times cosine omega ct, but I have to evaluate this at 0 and t, which is equal to minus v naught over omega c. At t equal to 0, that's correct, but at t equal to 0, sorry, at t it is the same thing, but at t equal to 0, I should put in v naught over omega c. So that piece I was missing there. That's the way to say it. Okay, and yeah, let me squeeze the next one in. Now let's say at t equal to 0, what happens? Oh, this one is plus, right? Sorry. So at t equal to 0, what happens? This to cancel out. So x naught. So at t equal to 0, x of 0 is equal to 0. That implies that x naught is equal to 0. So x naught is still 0, but I was missing this term. I was trying to put that back in x naught itself. So x naught is still the position at time t equal to 0, but now we have this new expression. So what's our xt can be written as, with the definition that this is r. So r is equal to v naught over omega c. Sorry about this confusion. I'll write this as minus r is equal to minus r cosine omega ct. Okay. I'll take 5 more minutes. I'll try not to do this very often, but since I'm making this error, I'll take more time. Okay. Hopefully I can finish this. Okay. So do the same thing for y. This time it is sine omega ct, and here the next term doesn't really contribute because at t equal to 0, sine omega t is 0. Again, use the condition that at t equal to 0, y of 0 is equal to 0 at t equal to 0. That implies that y naught is equal to 0. So our equations are, our equation here becomes y as a function of time is equal to r sine omega t. Let me put this both together. X of t minus r, so I brought the r to the left, is equal to r or minus r cosine omega t. And y of t, let me write this as minus 0, is equal to r sine omega ct. Again, exactly like the velocity, let me square these quantities because there's a cosine and sine coming, and if you square them and add them, that leads to a 1. So that seems to suggest that x as a function of time minus r squared plus y as a function of time squared is equal to radius squared. And that's an equation of a circle, but equation of a circle with whose center is, maybe write this in this form, minus 0 squared is equal to r squared, whose center of the circle is r. That's your center of the circle. That tells you that, oh, that's the radius of the circle. Right? So remember again, this was your diagram. The particle started from here and then started going in a circle, came back here. So that's the center of the circle. That's r comma 0. Is that visible that I'm writing? Okay, so that's r comma 0. It started from here. If that is the center, so that means the radius of the circle is r. And that proves that in a magnetic field, things go in a circle. Of course, if it is a negative charge, you're familiar that it will go in the other way, right? And there's a nice experiment that does that. Actually, this was a very common thing. That's how beta decay was, or a neutrino was discovered in this manner. So this is a very easy setup you can do. So what they do is that you take a big, or not necessarily big, you take a box of a cloud, like this is a humid, let's call it a lot of humidity. If you notice that sometimes on a clear day, whenever fighter jets go around, they leave a streak of white, what do we call it? So it's basically condensation of air where the flight is going through. Like if you have a high energy beam going through, if it is cold outside, it can condense around that region. So exactly what happens is that if you put in a beam of charged particle here, and because let's say this is a neutrino, or it could be a neutron, right? So actually a neutron, let's say, right? A neutron, it won't be visible, right? Because they are small, tiny, right? So these are not visible here. But suddenly a neutron can decay into a proton and an electron. And now if there is a magnetic field, let's say going into the room, a proton will, what is the proton? The proton is positively charged. So positively charged this way, right? So proton will positively charge. So that's positive and a negative charge is created. A proton radius will be larger, right? So proton radius will be large like this. And an electron will make a small circle. And how do you see that? Because it forms a cloud there, like condensation will happen there. This is called a cloud chamber. Even now, this is very standard way of detecting high energy particles. Like you just put it in a cloud chamber and they form this. Okay, I should stop here. Thank you. Oh, some of you guys already left. I was delaying. Yeah, I'll not do this very often, taking more time. Yeah.
All right, have a good one.
Yeah, okay.
Thank you,
Enjoy.
Professor.
Yeah, good. Wahid, how was it?
I was okay. I was like, I was like really focusing on the math. I wasn't focusing on the physics, sort of, but
Yeah, I think most of the
Yeah.
course deals with more of the math and less of the physics, I guess. But it's good to, since math is a new part, I think it's a harder one in the psi concept.
yeah, I mean, the cyclotron, it's like an interesting concept. It's like, I mean, not too complicated.
Yeah. Yeah, do submit the assignments, okay, or the quiz, right? That's an easy way of scoring, remember.
I did, I submitted I actually have a question. I submitted that quiz. You said to explain what a cyclotron is, right?
Yes, that's all. Mhm.
So I just put like some random facts and like some mathematics.
That's all you need. That's all I need. Yeah.
Oh,
Any
okay.
random facts concerning cyclotron, of course.
Yeah.
Okay. Enjoy, guys. Yeah.
Thank you.
Yeah. Bye, Christian.
Oh, did you see I sent the NCUR email to you?
Yes, I did get that. Thank you. Yeah. I was just pointing that out. I was not, yeah, you got my, but yeah, thanks.
Yeah. No, of course. Yeah.
I wanted to look into it and I do. Yeah. Basically, I have a friend, I think, who's part of this NCR. I just want to forward that to him. That's all. I would like to know what is the guideline or what is the requirement in this. I think at least they should write more of it. There should be some more information.
Yeah, because all they put was here's like what our grading criteria is in the broadest sense, basically. But
It's not very helpful, right?
I agree. But yeah, and I saw the email that you sent to me and Avinash. I didn't read the attachment, so I didn't really have time because I was going to lunch. But I saw that you said it was like a 3-minute presentation.
Yeah. So here's basically it is for PhD student, graduate students. What they ask is that so it's a competition. There is a cash award for that, about $800 or something. So there is a motivation there. So you make one PowerPoint slide and explain your research in 3 minutes. Right. So that's the goal of the presentation, and you're assessed. And if you win the first prize, you get $800, and there are some more prizes in there. But I was thinking that it's just a good thing to make, right? So you make one PowerPoint and explain your stuff in 3 minutes. It could be challenging,
right?
But take liberties there, since if you're not submitting to anyone, so take it. And then I was thinking, okay, what's the motivation? I would say I'll post it on some web page, let's say my web page or something like that. So it can be advertised in that sense. It's a good thing to do, I think. So try to do that.
Yeah, I think that is because it's always hard to kind of condense your research and just talk about the main points that you need to get across. So I do think that would be a good exercise, I guess you could call it.
Exactly. Yeah. So I thought it's something okay to ask for. So yeah. So try that.
Yeah. And I mean, I'm making a 10-minute one anyway, so it shouldn't be too much. Yeah.
That's why I put the deadline as March 31st, so that you're right in that spirit. So you just finish it off there. Yeah. Okay. Yeah.
Oh, and
Very
if you
yeah, go ahead.
If you do need help carrying some of the camera equipment or something like that, I could stop by Necker's and help you carry stuff over to class.
If you help me out on Monday, I don't know how things are going to be. So on Monday, if you could just come by my office, let's say, I think we should get out early, let's say at 45, 15 minutes before, let's say, get out. If you could help me just on Monday, I just want to see how bad it is.
Yeah, no problem.
That would help, and then you could move with the stuff, and then I'll come behind you, or something like that. That would surely. Thank you for that. That's nice gesture. Yeah.
Okay.
But I want to find a permanent solution, like some bag or something that I can easily carry instead of depending.
Yeah, I have some extra boxes and bags and stuff laying around, so I'll bring something with me too. So.
Yeah, sure. Yeah, do something like that, and I will try to get something. I'll see. I don't know what I'll do. This weekend, that's a small, tiny project I have that I figure out. So I measured the sizes so that I can do that. Yeah, some small price you have to give for the change of class or enrollment. Yeah, but I think it's okay. Yeah.
Okay.
Okay.
Thank you.
Hey, Bowden. Hey, Christian. Bowden wants to say something.
Yep.
Did you get the email about next week? There's that like RSO fair.
Was it from Dr. Mazumdar?
No, I think actually maybe it was sent earlier this week.
Oh, okay. I don't think I saw that one. I saw the one from Dr. Mazumdar about funding.
Yeah, it's the thing they do at the beginning of every semester. Like you send in a representative, just kind of like be there. I was going to ask if you could do one of those dates because I'm not available for any of those times.
Yeah, that's fine. What day is it?
It's either Monday, Wednesday, or Friday. I can resend the email.
Okay. Yeah, I'm
Usually-
sure I have it in there somewhere. I probably just overlooked it. Yeah.
Okay.
Okay. Yeah, I'll look into it right now, and then if I don't find it or anything, I'll just shoot you a text.
Okay, I'm good.
Okay. All right. See you guys.
Okay, bye, Christian. See you.
Yeah, I just have a quick question.
Yeah, sure.
I was thinking about